So this problem is quite similar to previous problem 4.79. So you can check that and then come to this. So in this problem, we have a disk that is hanging by elastic thread and the disk itself is kept in a chamber with some gas. Now this disk performs torsional oscillations. Moment of inertia is I. The gap between the disk and the planes is h. So this gap is h. So on the top the gap is h and the bottom also gap is h. Find the viscosity of the gas if oscillation period is t and logarithmic damping decrement is lambda. So when you turn this disk, there will be two torques that will act on the disk. One is due to the elastic nature of the thread and that will be proportional to the angle turned. And second will be viscous force that's going to resist the motion. So we'll calculate both of those torques separately and then add them just like how we did in the previous problem. So in the previous problem, the viscous force was given to us. Here it's not. So we know the viscous force is given by eta dV by dz. So this is viscous force per unit area on any element. So dV by dz is the velocity gradient. Now velocity of any element on this disk will change with radius, but at a distance x, velocity will be constant. So let's take a small ring element. On that, the velocity will be constant. So on that, viscous force will also be constant. So let's find a small torque based on that. So from this mean position, if the disk is at an angle phi, and let's say its velocity is v, that is phi dot x. So the elastic force will be minus alpha phi. So alpha I'm just assuming to be a constant. So and second force due to the viscous nature, that will be F1 into dA. So this F1 is force per unit area. So on this whole ring, tangential force will be F1 dA. So just like in the previous problem, we have taken phi in this direction to be positive. So top direction is taken as positive. So both the torques due to the elastic nature and due to this viscous nature, both will be downwards. So both will be negative. So N1 is minus alpha phi and dN2, so a small torque due to the viscous force on the ring, will be minus F1 dA into x. Now F1 is eta dV by dz. So velocity will be phi dot x. Z will be height. So dV by dz will be phi dot x by h. So F1 is eta into phi dot x by h. Area. So area, we have to take the top area and the bottom area of the disk as well, because the viscous force will act on the top of the disk and bottom of the disk. So area becomes twice the area of the ring. So twice of 2 pi x dx times x. So now we have got the torque as a function of x. We integrate from 0 to r, and this will be the torque due to the viscous nature of gases. So net torque will be I alpha, that is N1 plus N2. So we put those values of N1 and N2, we'll bring them on the left side, and this becomes our equation. So this is the standard damped oscillation equation. The coefficient of phi dot is 2 beta. So beta is half of this. And they have given lambda and t to us. So let's write beta in terms of lambda and t. So we know lambda is equal to beta t. So this term becomes lambda by t. So from here we get the velocity of, so the value of viscosity. So it's a nice experiment to know what is the viscosity of a particular gas. All right.